since it's about 5 after, we should get going. Anybody want to discuss what they were able to achieve, do, challenges with respect to the competition, the rainforest connection species audio competition is what we are engaged in. Anything people want to share?
Yeah, I could show what I've got so far and discuss a bit what I'm going to do next and maybe ask for your opinions on this.
Yep, sounds good, Dato. Go for it.
Okay, so in just a moment, let me share my screen. Okay, here. First, I will show the initial exploratory notebook I've used to have a look at the task here. So I'm using Fast Audio. It's a library. We saw this before in some notebooks. Srinivas showed us. So yeah, so here it's like everything is pretty straightforward. We get everything into a data frame, and in this notebook I only work with true positive labels, haven't incorporated those negatives yet. Okay, so first I just join the labels because we have like a separate row for each file, like not for each file, but for each label here. So we should group by recording ID if we want to have like one row per recording. So that's what I do. And here I inspect how many recordings have multiple labels and like what other. And here you can see that there are only 67 entries with multiple labels. And in many cases, here the label is the same. So it's like two moments in time when we have this particular species sound at the recording, right? So, but also there are some labels like this one. Here you can see that there are 3 species present in one file. And yeah, so then I look at how many are there of these files where there are multiple species, and you can see that those are not many. Yeah. Okay, so and yeah, and again, in many cases there are like still repetition of the same species in a file. And yeah, so then just the matrix we use for this competition, it's not present in FastAI, but it's in scikit-learn, and we can easily create a FastAI matrix, FastAI compatible matrix from scikit-learn by using, yeah, so here it's defined there is.
Ato?
Yep.
One comment on this, and because just last night I was playing with trying to and then found some links. One comment I have is the sklearn LRAP metric is yet again just a little bit different from the metric that the competition uses. And the difference is the first two words, label weighting. So the competition uses LWLRAP, label weighted, label ranked average precision. So the difference between the LW and this one is the fact that, let's say, again, I'll post a link that kind of touches on this, and also how to best, somebody has actually posted, I think, or at least pointed to how you can easily still bring in or code LWLRAP in FastAI. But the point being that the LW part, what happens is, if let's say you have 3 species and you have 2 positives for the first one, 1 for the second, and 3 for the third, the LRAP will treat each of them as 111 in terms of its weighting, whereas the LWLRAP, what it will do is it will weight it in the ratio of 2:1:3.
Oh, okay, that's useful. And I guess you can probably just fit here this sample weight, right? And it will work or not?
I'm not really sure about that. I'll have to look at the SKM code. My understanding, and again, yeah, see, the sklearn import is the label ranking average precision, and what it lacks is the first part, which is the label weighted label ranking.
Okay. Yeah, should probably inspect what the sample weight does here. Yeah, but
yeah,
let's move on with that. I think.
Yeah, just a comment that you may want to look at that, and I'll also look at what sample weights does. I haven't looked at that part.
Yeah, thanks. I haven't yet got to submission, so we just haven't discovered that fact yet. I haven't submitted anything to the competition. So yeah, here, yeah, I use this fmin and fmax as it was done in the previous notebook. You showed at the previous session to define a spectrogram, and this basic MEL spectrogram, it comes from Fast Audio, and I think it uses torch audio behind the scene. So, and I took some hyperparameters here from that report we discussed before, and yeah, so this might be fine-tuned, because that report was not for this competition, but for that other data set, which has, I think, like 5-second long audios or something like that. Yeah, so with that, we define this data block and data loaders. We can there are handy functions in FastAI and Fast Audio to view these spectrograms with labels here. And yeah, you can see that those are quite different. It would be even better if we plot like this T-min and T-max here, I guess. I'll probably have a look at how you can do this at some point of time, just to highlight their time interval of interest. It would be useful, I guess, but it's not here yet. And then it's just standard CNN learner based on ResNet 18, and we can plug in basically any model here, any like vision model, and probably by moving from ResNet 18, which is the simplest one, to something more performant, we can like have some gain already. But yeah, that's a long way to go before that. And I use this accuracy and LRAP, and accuracy is not very useful at all here, probably because I don't know, most of the time we have just zeros everywhere, and probably model learns to predict those zeros, but that's not really informative. Maybe some other metrics like F1 or F beta would be useful here. We could try it also, like to get some additional information of how the model performs together with this LRAP, and we will, as Srinivas said, that this one also to be reviewed, and either we need to redefine it or maybe just feed sample weights. Yeah, we'll see. So here I just use the whole audio file. So the size is of the resulting image is quite large. So I use gradient accumulation here because the actual batch size is smaller. Okay, and with that we do some fitting, and yep. So okay, and let me find.
I thought to one other comment, since you were talking about the size of the image. So in the notebook that originally Steve had used and that I kind of went through, I think last week or week before, I forget now, but that's one of the changes or improvements, and you already spoke about it, but just wanted to highlight that what seems to be a more common approach, I don't know that whether it is ending up winning, we'll see whether we can push it as high as some of the winners, but seems a more common approach is to take a slice of the input around about a 10-second slice around a label that's there in the input, and then train on those 10-second slices from each of the rows in the input, because as you showed before, you combined all of the species in a row into the same row. What the other notebook did was to train take a 10-second sample around, making that the center of a 10-second sample, the center being at the middle of the Tmin Tmax for the label, and then using that to train. But then when it comes time for prediction, obviously you'll need to predict over the entire 60 seconds. And the way it does that is then to chunk the test output into 10-second chunks as well, and then just combine it.
Yeah, I remember that discussion from the previous session, and I will, so here I did this intentionally, basically, and I will explain the intention a bit further. So here, yeah, the output of training is not stored, but I can tell you that with these settings. So first I just do a couple of epochs fitting the head of the model. And after that, I do 40 epochs with mix-up, of training with mix-up, with a bit lower learning rate. And here, this resulted in about 80 LREP, but as we discussed, this is not really relevant yet, because I don't know how would it map to this LW rep, LREP, right? So but again, that's not the point here. Just like fit in. But yeah, from what I take from here again, and I think I mentioned it before, that mix-up seems to work great for this kind of task. And so the model was not really overfitting as I trained for quite a while. Yeah, it was.
Yeah,
not
I think I would echo what you're saying there. I haven't applied it yet, but mix-up seems to be a handy thing to put into the mix. So I agree with you. I think that seems, I haven't done it, but it's high on the list of things which does seem to have a very positive impact.
Also, in FastAI, you have this interpretation tools, and I did like tried some of that. I've checked if the model finds those false positives, and yeah, we discussed that before also, that actually the wrong predictions were usually not the false positives from there. So that's something I'm not sure how do we interpret that, but yeah. And finally, what was I like going to get here? This is GradCam. So I use this library called PyTorch GradCam. Here you can install it like this from pip, and here are some like this some of these GradCams, and as you can see that for most images the model attends everywhere, right? So for example, here it like looks almost everywhere. Yeah, so the maybe like I'm not sure if the patterns are quite comparable between these pictures, because as you can see here, I plot here, this is a spectrogram for particular track, and this is output of GradCam, right? And it shows basically which areas the model uses to produce the prediction. And for example, for this image, as you can see, it actually like looks somewhere quite a bit more than to other places, but yeah, most of the time it actually looks at all of the track, and that's not really good, I guess, because as we saw, actually the label is only just a tiny part of this. The label is like relevant to only a tiny part of this. So that's something to play with, this GradCam scene. It's quite easy to use and probably may provide like really useful insights into what's going on in the model. And so these different patterns are obtained for different layers of the ResNet. And I guess usually the most informative results of this GradCam are from the later layers. So this one, the first one. Okay, so that's
yeah, the GradCam analysis is very interesting, because I think, yeah, if we also kind of add the time scale, then ideally, if I understand the computation correctly, then ideally you would, in the perfectly ideal situation, you would want the GradCam to indicate that it's heavily focused on the Tmin, Tmax, and not anywhere else, right?
Yeah. So that's like basically quite what we expected, right? That the naively feeding the whole spectrogram into the model would be like basically model cannot distinguish like the useful signal from the noise, and maybe it would be a really hard task for a human to do if you just provide it with labels and 60-second audio, and you need to find somehow the relevant part of the track. That wouldn't be easy. So what I think to do next is instead of slicing the file into sub pieces, and here is I want some input from those more experienced with convolutional neural networks and vision applications in general. So the idea is to instead of doing it in slices, we could still feed the full image into the network, but instead of having like a single label for like now we have a label of size of number of classes, 24 in this case. But what if we, so here I define this function to produce labels, maybe just let me show it. Okay, I probably have it. Just 1 second. Okay, so this is a label, and it has 11 rows, which would correspond to, so each row is would correspond to a 10-second piece from the audio, and I do it just in I have this sliding window over the input, right? We have 60 seconds, and we have this 11 overlapping frames, and for each frame we have all zeros if no signal is present there, and we'll put 1 here for the cell where we have the label. And as you can see here, in this case, because the frames are overlapping, we have like multiple parts of it where the label is 1. And this corresponds to 14th, in this case, 14th class of the species.
Atto, when you say the frames are overlapping, you're taking, if I understand correctly, you're taking 10, since you have a range of 0 to 11 or to 11, you're taking 10 slices of the 10 overlapping or 10 windows, right? And do you, you're overlapping by some amount when you shift the windows?
Yeah, by 5 seconds. So each frame would be like, so the first frame starts at second 0 and ends at second 10, and the next frame is at second 5 to second 15, and so on. And
okay. I see. That's where the overlap comes from. Okay, got it.
Yeah, and that would be like a hyperparameter. Here we can overlap by more or less depending on what results are. I'm still not so sure if this approach would work at all. So because I haven't finished it yet and haven't tried to run it. And also here I calculate like the total duration of the sound, and I have some minimum overlap if the frames overlaps but less than this amount, which would also be probably hyperparameter, because I'm not sure how this would affect the training. Then we assign the label, right? So those are the labels produced, and in this case we want also a specific head for the model, right? Because right now the model would output like in FastAI standard. What we do is we have what they call adaptive concat pooling, which does adaptive average pooling and adaptive max pooling, and then concats those two. But we want to change that to produce in this case, and this might change. We could like make more of these frames or less, but in this case we want to produce 11 like outputs from this from the output. So let me just quickly show you probably what this is supposed to mean. So the output from ResNet, like the convolutional part, which is called body here, would be, we have 512 features, and we have 4 by 176 the output is of size 4 by 176, and this two last dimension have like this geometric interpretation, right? That would be what comes from our image, but the size is decreased by the strided convolution, right? And instead of doing average pooling over all of this,
sorry, could you repeat the dimensions there? So you're saying 512 is what now?
512 is number of features or like number of channels, right?
Right. And then is it height by, is it H and W that you're saying is 4 and 176?
Yeah, that would be what comes from this like special dimension, because like our original image.
Eventually, what results from the output of all those convolutions, private convolutions that you do. Okay, so it is H by W, right? That you're talking about over there.
We had like a long image for our spectrogram, right? Because it's a long audio, and
correct.
And now we can do this adaptive whatever pooling. This basically is also in here we have an option to do this pooling in different, like we can do again this adaptive concat pooling as it's done by FastAI, or there are some other pooling functions, something like I don't know, power or energy pooling, it's called something like that. It's available in PyTorch, but I'm just like for a start, I want to like see if all this works at all, but and then you can play, like make a more elaborated head here and try it out. And then I just so now we obtain where we had 4 by 176. We do an average pooling here, and we want 1 by 11 because we have 11 labels, right? So we want to have 11 outputs from our model. And then so now we have like 512 by 11. I want to transpose it to get 11 to be the second dimension and 512 the last dimension, because that's kind of our features. And yeah, so then I do simple projection from the feature dimension to the number of classes, and you can like add another linear layer here if you want, or if you need it, but you get the idea, right? To make it, and yeah, so here this is where I am now. I just need to yeah, so I was trying to put all this into CNN Learner, and I guess it's doable. But if not, probably you would have to define your learner like manually, but that's not really super important. So for now, I have some dimension mismatch here. Maybe I just missed something, or I just forgot to put here an in. So yeah, I will not hold the attention longer. So that's what I get, and I would be interested in comments of why this approach might not work, or something. If you think that slicing is like slicing the image as was done in that notebook we considered before, would be beneficial in some way. So and again here, instead of binary cross entropy, you can use focal loss, because we basically have a label where most of the time we have 0, and only occasionally we have like positive labels, right? And focal loss is designed to work in that case, as Srinivas suggested in the previous session. It would probably be a good fit here. Right, so
one question I had, Atop, in your mind, what advantage does the overlapping of the slices do as you, and you're still training per slice though, correct?
So I'm training for
Meaning,
the whole image. So so the intent of having the image as a whole here is to like basically it's first like more computationally efficient, because we do just well, computationally efficient if you want to fit all the parts of the image into your model. Okay, now it's working. Nice. And the second is I just like it appeared to me that this task, if formulated in this way, kind of resembles the object detection problem, and kind of really simple object detection problem, because we have like we don't need to worry about aligning those anchor boxes as done in actual object detection. We just need to find their place in time where the signal appears, and I think in this formulation it's kind of more flexible in some way, because you can probably somehow add information on false positives here, and maybe analyze the results in more like rigorous way, because you have information from all that image, and you kind of you feed the information that most of the noise we observe everywhere, it's not the signal, right? So one thing that was like curious for me here, although the network attends like everywhere, right? So the at least each bit, like most of the image has some response on the gradient of the output here. It had like I'm now that you told me that LRAP from scikit-learn doesn't work here, I'm not sure about that, but I think it like produced a fairly fine result, and maybe there are some patterns associated with like not with the actual voice, like not from the actual song of the particular species, but also from the background this associated with species, and in this formulation, I guess we could try to find if it's true or not, if the model can like utilize the information from the background or not, and also it's like questionable if this information is present, do we want to use it or not, like not in the like from competition point of view, but in general, right? So if you have some leaking information, but it's not actually what you are looking for, should you use it or not? Because the network might rely on it, but on this change of the circumstances, this information won't be present any longer, and you will have to like retrain, and the network will fail, right? So those are my thoughts, and now I'm happy to hear yours on this point.
A couple of comments, right? One is actually I didn't say, I mean, to be precise, I didn't say that LRAP was wrong as much as it's not exactly the same as what the competition uses. So your LRAP might still give you a very good indication of, or even a much better indication than accuracy of kind of the leaderboard score, if you will, than accuracy. But I was just pointing out it's probably not exact, subject to us evaluating, what the weights do, because there is a label weighting that's applied in case of the competition. But LRAP might still give you a much better indication. In fact, my reading generally says, again, to your point, and you already alluded to it, that F1 score is probably a better metric than accuracy to begin with. So your LRAP may be even better than accuracy. And so the key point is I was just pointing out that LW, LRAP, and LRAP are different. That's it. The second comment I had is, one of the things that with respect to the label thing, or two-part comment. One is, it's interesting because you're kind of saying that by using this approach, you allow the network, if I understand correctly, or at least it's possible the network would learn this lot of, for lack of a better word, noise or silence with only a few positive examples, right? That's kind of what you were, did I understand that correctly?
Yeah. So I think by feeding like a lot of this noise, all the noise we have, right? We provide some information to the network that this is the noise, right?
Right. That it doesn't. So two things I saw, three things I saw as I was poking around and playing with things and stuff was, one is, so I mean, again, I'll just throw it out in no particular order of the top of my head. One is, I saw somewhere or some people trying to do something like use the model to predict and then see whether it predicted positive things where there was just noise, right? Meaning, if it kind of is the model generating a lot of false positives? That is, it's recognizing sounds where there is actually noise. I thought that was kind of interesting, just as a comment, that would be interesting to see whether the model recognizes a lot of positives where there aren't. The other comment, and we haven't, to your point, none of us have gone to the point of saying, okay, how do we use the false positives? And that's again a completely separate problem, because I think the in the false positive case, what the data that's provided actually is, they are explicitly telling you that these portions of the sound are not corresponding to these species. And somewhere, and again, that's a whole another discussion, especially since many of us have also been in the deep learning PyTorch course. One idea that came to me, and I saw some postings, I haven't yet dug into it because that's advanced stuff, and I want to get through the simple things we can do, is there the whole contrastive learning approach comes to mind, because you now have positive examples from the TP files and negative examples of the same species from the FP files. And by doing something like the contrastive learning, where you provide, positive examples and say these are good, and negative examples and say these are bad, maybe that approach might work to make use of the false positive data as well. That's provided to us. But that's a whole separate path that I haven't yet even begun to think about or go down. That seems to be, a very applicable thing for contrastive learning to help out. That is, true positives are positives which are true, and then false positives are positives that are false. So by making false positive high energy and true positives low energy in this energy example contrastive learning approaches, maybe we can really learn a model that's good. But that's the extent of my thinking, and we have to I still have to see how to practically bring that to fruition.
Yeah, that's really interesting part of this competition, to look at this from the point of view of how do we use this false positives. And another approach which comes to mind from the areas with which I'm more familiar, and here adversarial training might be useful in this case. Like in language modeling, there are a lot of data sets, like adversarial data sets, for example, there is natural language inference task when you are to determine whether the you have given premise and hypothesis, you need to find if one is entailment or neutral or contradiction. And there are a bunch of adversarial data sets where these examples are made really complicated on purpose and controversial from a point of view of a model and also of a human. And there are some success in applying adversarial training to you do not train explicitly to on this adversarial stuff, you don't do anything explicitly to tell that pay more attention to its adversarial example, it's say false positive, but you just play with the gradients and you optimize your training from information theoretic perspective, or from the perspective of how the change in input affects the output. So you try to find this smoother loss landscape. And yeah, so it would be interesting to have a look if this could be applied here.
Hi, this is Alex here from Singapore. So actually it's my first time joining this Kaggle session, and I just come across this session today. So even now I still looking through the material. So I don't think I have something to share, but I think I can give some comments about the difference between LREP and LWREP. From what I see, I think the difference mainly lies on the way they aggregate the matrix into the score. So essentially for the LREP that we see in sklearn, so mainly they do the average over the instance. But for LWREP, they try to separate out each label and do the average. So I think that's so that's the main difference. So to illustrate this, maybe I can try to illustrate in a whiteboard. to quickly tell the difference. So can you guys see the whiteboard?
Yes.
So let's say a simplest example is, so you can, because at the end, we can represent the score into a matrix. Essentially, the row is the instance, the column is the class. So we can represent it, each instance, by some score. Let's say we only have 3 class and 3 label, 3 sample. So let's say for the first class, the score is 1. It's something like this. So this score essentially is the ranking score. So it means that this class has the first sample has free ground truth class, but they have different score. And the same for second and third. So if you do in a LREP way, right? So what we do is we try to condense the score for each sample. So in the first sample, you get something like 1 plus 0.66.33 and then divided by 3. And then you get 1 score for this sample. And you apply the same logic for the second sample. In this case, will be 1. And the same logic for the third. So once you assign a score for every instance, then you can average them out. So that's how it works for LREP. For LWREP, so they will be even simpler. Essentially, you just average out the whole matrix. So the consequence is that if you do it in an LREP way, you will downweight the contribution of a label if it is a multi-label in a sample. And in the LWREP way, you try to equally weight each label, no matter it is a multi-label or a single label. So I think it will only make a difference when we do a multi-labeling. From this problem, I think it is a multi-label, but it seems like most of the case are single label. So my feeling is that it won't impact much, but I think I need some experiment to verify that. Yeah, I think that's what I want to give a comment about.
Yep, you're right. It's weighted by the occurrence of the labels. So if you have more of a particular labels, then in case of LW, LRAP, it will normalize to that, but as LRAP will not. So yeah, I think that's why I was saying earlier that to Arto that LRAP would still probably be a much better indication than accuracy or even F1, but I was just pointing out that there is a difference between LRAP and LRAP.
Yeah, I hope the explanation helped. And also I think is it R2? Yeah, so you write a custom function to implement the LRAP in FastAI, right? And you have a sample weight. So I think in this case, sample weight could not implement the LWRAP. So probably you need to slightly calibrate the code in order to achieve that. But I think it'll be a simple tweak, just changing the average over. You just change the 1 line of code. Like when I see some example from the Kaggle, they do some implementation between LRAP and LWRAP. The only difference is only 1 line of code. So I think it's not difficult to change LRAP into LWRAP. So yeah, so that's what I want to give a comment on, and I hope it helps.
I think that
thanks.
Really clarifies it.
Okay, thanks. Alex. Anybody else on anything else they attempted? Yuri, Steve?
I haven't made any progress this week apart from watching a few more videos from the guy on YouTube. So I actually understand what I'm doing now. So I just need to put it into practice.
Yeah, I think those videos are pretty helpful. I still have to go through some of them. Yuri, go ahead. Can't hear you, Yuri. Still can't hear you. Okay. Okay, so I played with a variation of a notebook, and I just wanted to kind of share that. If nobody else had any other thing they wanted to share, I can do that. Let me share my screen. Yeah, that's the one. Let me know when you folks can see it.
Yep.
Okay, so this is a variation of the notebook that I had already used, which, as I mentioned to you, to Arto before. So the basic approach is still the same, which is to train with a 10-second chunk around Tmin, Tmax of every recording and do the validation using the 10-second, using the same chunks, and then do a prediction on the entire 60 by 60-second test sound frame. So we'll refer to the 10-second as a chunk or a clip and the full thing as a frame. So it's, you train on clips, you predict on the frame by just clipping the frame, the test frames into 6 consecutive chunks, no overlaps, and then just max predict on combining the max predictions on each of that. And then you train on, and then you do the whole thing on a stratified k-fold, where the fold is 5 folds, and you just average the prediction on the 5 folds. So that's what the previous notebook does, and you can, I kind of pointed to the link of that. But that got us, as I shared earlier, to about, I think I got lucky, even my single fold got me to about 0.775 something. So the 2 other enhancements, and they were interesting because I wanted to get into the details of the enhancement as well, and I can share a little bit of that. That this notebook does is one, and I haven't done the ablation study to see how much comes from each of the changes. As you can see, the score that I submitted and got is now in the mid 80s. So it's about 0.85 versus 0.75 for my previous submission. So the 2 additional things that this notebook does is, one, it uses augmenting on the 10-second chunks of MEL spectrograms. So it applies some augmentation to the input, A, and B, it uses a special optimizer. Now, the details again of that optimizer, it's an adaptive stepped optimizer. And when I post a link to the notebook, you'll also see a link to the paper. As we do typically, I think I've jotted it down without spending too much time right now on the details on the paper. This is one of the things we typically do at the end of the competition, is go through all the relevant papers for high achieving notebooks and kind of learn the techniques. So we'll defer the paper discussion, but if you're interested, the link is there in the notebook itself. So the couple of things that this notebook does, as I said, is apply a set of augmentations. These are the augmentations. The first two are fairly simple, right? It's just flipping the image horizontally or vertically. And that, in this case, I guess both should be okay, because there's no, as long as it recognizes the particular frequency from the MEL frequency spectrogram, shouldn't matter with respect to the flip. Sorry, question?
If you flip vertically, does that not change all the frequencies? Because of the fact that frequencies in the MEL spectrogram, they're in particular bands on the image. If you stick the thing upside down, does that not swap all the frequencies about?
Yeah, it would flip, but the question is, like when it predicts, I was thinking of it in the situation of ultimately it's looking at the amplitude and where the amplitude is located, right? Meaning the intensity. But it's a good question as to whether, I was wondering about that myself too. And it's the same thing in reverse with respect to the horizontal flip too, right? Because the time thing is flipped when you do the horizontal flip. But the time thing may not. Go ahead.
If you had say a bird or whatever whose call sort of increased in frequency from start to finish, and you flip it horizontally, then you're making it obviously go the different way, which could be a different bird. Similarly, flipping vertically, if you have a bird that's got a very deep call, suddenly it becomes a very high pitched call, doesn't it? So
yeah. So that's good. So I have to investigate that a bit more, but at least naively what you're saying makes sense, and I was wondering about that myself. The others, the other ones, and all of these are, by the way, from SK Image, and there are different ways that I've seen for applying the augmentations. There's audio augmentations. I think there's a whole library of them called Augmentations or something, but this seemed to be simple enough and at least understandable to me as to what is actually happening. So in that sense, these are simple starts, but there may be more fancier ones and libraries for audio augmentation that I haven't yet got to. The noise just adds random noise, and again, the random noise happens, if I recall correctly, to be Gaussian noise added to the input. If you see the code, I'll just jump to one part of the code. If you see these add channels, it basically stacks and creates a 3-channel input from a single channel input, right? So in a sense, the way he uses the way things are set up in the notebook is he always applies these add channels at the end of any of these. I mean, you can do it a bunch of different ways, but just to call your attention to the way this notebook does it is, therefore, after you're applied any one of these augmentations, you just make sure that what you're returning is actually a 3-channel output, even though the input going in is your basic image, which is a single channel from your MEL spectrogram. The output, because everywhere he does add channels to this, and add channels just basically stacks the 3. So that's what returns. So this is add noisy, which adds noise. I thought this was interesting too. So contrast stretching, what it does, and this whole exposure thing is it deals with rescaling the amplitude or rescaling. I say the amplitude, but it could be the power as well, as we discussed last week. It's rescaling the values that are actually plotted on the image. It's not the frequency and not the time. It's actual intensity or amplitude or power, because that's what is plotted. That's the value of the colors that you see in a MEL spectrogram. And this thing helps you scale it. So you can scale it from 20 to 90% or blah, blah, blah. If you go again and look at the details of exposure.contrast stretching, let's see whether this is address log, but if you did, what's this one? This is, I'll just do. This guy. So this is what he's doing here, and you can see that what it does is after stretching or shrinking the intensity level. Can you see my screen?
Yep.
Yep.
Okay. Yeah. So the parameters are the array, and then you specify an input or output range for the image. And you can use whatever the min-max is in the image, or you can specify what you want, or you can use the data types min-max. And then, it just rescales it to what. So this one makes sense, right? Like, for example, if you say that, you understand something about the sounds of what you're looking at, then by rescaling the intensity, you would probably be focusing in on specific intensities overall that you might care about. So that at least does, to me, as an analogy to what we're trying to do here. So that's what contrast stretching is. The random Gaussian is Gaussian applied to, my apologies, there's some construction work going on in the background, but I can't avoid about the noise. The random Gaussian is Gaussian applied to the input. I haven't quite understood, because the random noise also is a Gaussian, so I haven't really, I do, sorry. What I figured out, although I should say I still would like to dig into the detail. What I did figure out, the difference between adding a noise, which is where you just add random noise, which is a Gaussian, is here the random Gaussian is actually a Gaussian filter applied to the image. So it applies a Gaussian filter in this case, whereas in this case, it adds Gaussian noise. Now, what applying a Gaussian filter does, you should go look at, and again, where does it, SK image filters import Gaussian. So you can go look at that to figure out what applying a Gaussian filter does. And it gives, I think you can give it a mean and a standard deviation and across the various dimensions, and you can use that, let that be a default one, default mean 0, variance 1, or you can specify it as you wish, and so on and so forth. And then the grayscale one, this one was a little bit confusing. So if any of you figure this out, I'll ask the question with respect to this, and then if you look into it in detail and you kind of can understand it better and explain it to me, that would be great. Here, what it does is, let's see, grayscale, it converts the RGB into, even though it's said to be gray, it converts it to the luminance values, if I understand or recall it correctly. So from SK image color, then you go to RGB to gray, right? So let's look at
but RGB has 3 channels and we have only 1 here.
Exactly. That's my confusion. Or if you SK image color, okay, there, and then RGB, see, there's a gray to RGB too, that you can kind of go that direction, but that is the RGB to gray, right? And if I recall it correctly, is that the one that we use? It is RGB to gray, yeah. So here, what to me seemed strange is he applies RGB to gray on the image and then add the channels. Going in, this image is single channel. So if it is single channel, although, you know, this thing says that it has to be array-like and the image is in RGB format, which I don't believe our input going in is. It's kind of in a single channel, which is not 3 channels. And then it converts it to luminance. I get that. But then it's supposed to raise a value error if the RGB is not at least 2D with a shape of, and the channels are 3. And then it converts it using this equation. Makes sense. But I don't quite get how that happens, or why there isn't an error if our input that we give is a single channel. So that's something I'm puzzled by. And if if you figure that out or know why it works, let me know. Gamma is again just adjusting the exposure of gamma. I think I have that. So gamma, and in another notebook I saw, sorry for the quick switching, but in another notebook I saw something called adjust log. And the reason I bring that up is this thing talks about how you can use gamma and log contrast, 2 different contrasts, and how you can drive contrast depending on how you apply the gamma correction and the logarithmic correction. The 2 seem to be either complementary or somewhat related. Okay, so that's all the different augmentations. And then the rest of it is very similar, except for he uses this particular optimizer called ADAS, which, and there's notebooks and links for where it's described as a GitHub location where all these, where it's described in detail. As I said, I haven't yet gone into that and read the paper. There's even an archive paper describing it. And just utilizing these changes, that is, if you just apply the augmentation and then use that particular optimizer with no changes to the basic structure that I already described to you, that is chunk or clip the training to 10 seconds around the label, and then when you predict on a take the max of the predictions across the entire frame, then that's it. And just doing those 2 things bumps up the score from about 0.75 to 0.85. I mean, you would have, we've gone through and seen all these code previously, and the only thing is, yeah, using this particular optimizer. And of course, the one other change, this is again not a major thing, although if I were to do ablation, I should probably do both Adam and this optimizer with the same scheduler. There is a scheduler change from the previous notebook. In this case, it uses the reduce LR on plateau, which means that after some number of cycles, if your loss of metric or whatever you're watching doesn't change, then you reduce the learning rate in order to get that to move along. And then you try, as I said, it's a 5-fold split. The other thing I was looking at was to see where it, I believe he uses, he applies any one of the augmentations. I'm just trying to see where that is. Yeah, so obviously if it is in test mode, you just convert it directly and you don't do any augmentations.
In the augmentations that he
So
has there,
here. Yes, go ahead.
Is it from that list there, the self.augs? Yeah,
yes,
because
yes.
it doesn't seem to have the RGB one in there, does it?
Did I? Yep, you're right. But so it does have the vertical and horizontal flips.
Yeah. But,
it may be called Grayscale, by the way.
Oh, is it?
Because
the sorry,
name
right.
sequence that might be called Grayscale. Is it called Grayscale?
I think it was, yeah.
Yeah, see. Yeah.
Right.
So it does. Yeah. He does have it, and then he makes a random choice of just one of them, because random choice just picks one of these augmentations. One of these. Yep. 1, 2, 3, 4, 5, 6, 7, 8. So 1/8 probability any one of them. And then, you know, the other thing I found puzzling, and you know, these are things we can clean up once it works, is he puts add channels as one of the augmentations too. Which if he is returning, if he's already doing add channels after every one of these, I don't see the point of this. Right?
Is that because of the fact that that needs to be done if you don't do augmentations? If you don't run the other augmentations, you need to convert it into the RGB 3-channel?
Yes, but that he would need to make sure he does that by making sure that every one of these has add channels, right?
Yeah, but if you are only picking one of those and you don't pick any of them, then the add channels isn't called.
But random choice is restricted to one of these though, right? It's not none of the above. I don't think it's a choice.
Yeah, but he doesn't want to apply augmentation every time. Sometimes you don't want to apply augmentation. In that case, you only apply add channels, right?
Yep.
But would that work here? Because he does augmentation all the time when it's trained though.
Yeah, but if he doesn't want to apply any augmentation, he still needs to do the add channels to get it into the right format.
Yes, but that he does here. You see that?
But that there's testing, isn't it?
That's the case.
Yeah,
right.
So like in training, he might apply like an augmentation, or he might just take the unaugmented image. But if he's taking like the image with no augmentation, he still needs to do the add channels. And so by sticking it in his list of augmentations.
Correct. I agree with you, Steve, but I'm saying, see, because again, this train label is provided as input whenever the thing is being trained. So as soon as if you look at the structure of the notebooks, when it calls the audio data, it's either for train or for test. Okay, and if it is for train, then these two lines always are used.
Yeah, but if he wants to train on an image with no augmentation.
Right, then he would need that. But I'm just saying there's no instance in which he actually does that, right?
It happens 1 over number of augmentations times, right? So it randomly chooses an augmentation, and at channels is chosen 1 over.
Correct. Yes. Oh, okay. I see. So you're just saying that it's one of the choices. So you just apply just the add channels in that instance where that's the only thing that's chosen. Okay, it took me a while to grasp that. Okay, got it. Got it. Sorry, as dense, which is why discussing with other people helps.
So what are the benefits of this ADAS optimizer? What's the idea behind it? Have you looked at it?
I think it basically adapts the step size. I didn't, did I have the bookmark? We can look at, because there is here. In fact, this is.
Is it something recent or?
It doesn't seem terribly recent. I didn't look at how recent it is, but here is the and I didn't quite grasp, and as I said, I didn't read the details of the paper. I couldn't, at least what this seems to say, I wasn't able to grasp immediately what it means, because here it seems to say that it fine-tunes the step size, right? And I guess he means that it dynamically fine-tunes the step size, because here he says this algorithm actually fine-tunes the step size, and then he says making step size scheduling obsolete. So these two things seem to mean that, unlike saying, for example, after so many things, reduce the learning rate or reduce the step size, it adaptively learns how to, or dynamically learns how to fine-tune the step size.
Yeah,
but
okay.
as I said,
but still he uses reduce LR on plateau scheduler there. So
yes,
that's
that's the thing which confused me, because he, as we saw, he uses LR on plateau, right?
yeah.
Yeah. So
not so obsolete,
that's,
or maybe that LR on plateau is just redundant.
yeah, which is why I said I've not, the things really to get to the bottom of it, which I haven't done, but I would like to do, is do the same thing with the same infrastructure and run with Adam, to just see and keep the LR on plateau and run it with Adam, and see how much of a difference in score, right? Because that would say, is there any substantial difference, or what's the difference coming from this ADAS thing as opposed to just the augmentations? And of course, the other one is what you suggested, which is remove the LRAW on plateau and just run with the ADAS and see what that gets you. And of course, the reality is just, dive into the paper and figure out how much of the, or what the details of what he's trying to do. But I just wanted to kind of continue with the same framework and try to push and see, where can I get to? Of course, there are a bunch of other enhancements to do on this, including what you pointed to, of the, the link around hyperparameter optimization. And then the final layer he uses is a lot simpler. The other thing which I saw in a couple of kind of exploratory analysis, explanation type of things is apparently the and this is where familiarity or deep familiarity with the domain space helps. Is apparently the spectrogram details matter, meaning how many Mel banks you have and what's kind of the shape of your Y and X and intensity. And that's something else worth exploring as well. And other thing which already you pointed to, is this notebook doesn't use mix-up at all, and I've seen mix-up be fairly important mechanism for getting score improvements. So those are all the different things that I think are worth further making improvements besides playing with what we have discussed and figuring out kind of through ablation studies what how much is the contribution of each of the factors. And I don't think let me see whether I have the link handy on yeah, I'll post the LWLRAP and how to implement it with FastAI that I saw on a link. I don't want to waste people's time as I search for it, but I did locate that as well, which is fairly interesting. There's a PyTorch implementation, and then there's a way to combine it with FastAI version 2 that I was able to locate. So that's it, and I'll again keep trying and pushing things and seeing what else are the various mechanisms by which we can continue to push the score upward towards the 90s. We know already that the best are in the 0.98 kind of category, so a ways to go to get there. Any comments or any other things to add from any? Okay, if not, thanks everybody for joining, and hopefully Ayush will be in a place to present. Oh, one more thing I wanted to, I think many of you are already aware, but we are launching a new study group on deep unsupervised learning based on a Berkeley course. So if you're interested, there is a new Slack channel, Deep Unsup 2021, that's formed, and we are commencing it at the class will be from 8 to 10 on Sunday mornings Pacific time. So if any of you are interested, sign up and for that as well. Okay, thanks everybody. Bye.
Cheers, thanks. See you next week.
Thank you. Bye.
Bye.
Yeah.